Today we're going to start Unit 4, which covers Chapter 8. Chapter 8 is all about hypothesis testing, which I'll get into in a second. Since you have an exam at the end of the week, this is the only video that I'll be posting this week. Hopefully that gives you a little more time to focus on studying for the Unit 3 exam, which only covers Chapters 6 and 7. So this stuff won't be on the exam, but Chapter 8 does build a lot on Chapter 7, as we'll see next week. But today we're just going to focus on Section 8.1, which is mostly about just making definitions of the terms that we need in hypothesis testing. So a hypothesis is a statement that something is supposed to be true, and a hypothesis can be either true or false. A hypothesis test involves two hypotheses, the null hypothesis and the alternative hypothesis, and we'll get into those more in a second. But generically, the null hypothesis, which is denoted like this, assumes some form of equality. So it will always be that some parameter that we're trying to measure is equal to some given value. So this can always be written with an equal sign. And I might read this null hypothesis symbol as either H0 or H0. You might also call it H null. All of those are fine. And we also have an alternative hypothesis that's denoted HA. And we'll get into what the alternative hypothesis looks like in just a second. But the goal is to design a hypothesis test to distinguish between these two and decide which one we think is more likely. I want to emphasize, though, that in all of these, we're never going to be certain that we've chosen the correct hypothesis. So we can never prove the null hypothesis or prove the alternative hypothesis. Instead, the goal is to determine which one seems more likely. And usually what we'll do is we'll determine a level of significance that we want. So we'll decide how much error we're willing to put up with. Let's say that we want a level of significance of something like 10%. What that would mean is that we have roughly a 10% chance that we've chosen the wrong hypothesis. And that's sort of an oversimplification, but that's the general idea. We want to minimize the probability that we're choosing the wrong hypothesis or choosing to support a false hypothesis. So let's look at what these hypotheses can take the form of. So in this section, we're just going to be focused on determining information about a population mean. So we're going to be measuring the population mean of some variable that we're concerned with. And the null hypothesis is always going to be that that mean is equal to some given or assumed value. So a null hypothesis will always look like this. The null hypothesis is that the population mean is equal to some given mu naught. And that will depend on the context of the problem. The alternative hypothesis is going to be that the actual population mean is going to be different from the specified or assumed value. So maybe a researcher believes that the population mean is not equal to the given mean, or maybe they believe that the population mean is actually larger than the specified value. So maybe just to give you an example of something like this, maybe you believe that the actual population mean per capita of, let's say, people infected with a certain disease is larger than what's being reported. Then in that case, mu naught would represent the reported values per capita for some country or whatever, and then your alternative hypothesis would be that the actual population mean is larger than the assumed population mean. So we could design a hypothesis test around that. The null hypothesis would look like this. It would just say that the actual population mean is the given mean, or this given specified value, and our alternative hypothesis would be that the actual population mean for whatever we're measuring is actually higher than that specified value. So we're going to look at determining which one of these seems more likely as we get into some experimental design for these. And then similarly, we might also hypothesize that mu is less than the specified value mu naught, and then your alternative hypothesis would look like this. But notice that in all of these cases, the alternative hypothesis is something like mu is not equal to the specified value, or mu is bigger than it, or mu is less than it. So the alternative hypothesis will always look like some sort of inequality, and the null hypothesis will always look like some form of equality. And these are all called either two-tailed or one-tailed, depending on which form your alternative hypothesis takes. So for example, in this one, we have a certain mu naught. The alternative hypothesis is that mu is not equal to mu naught. So the alternative hypothesis is that maybe mu lives over here, or maybe mu lives over here. And for that reason, this is called two-tailed. So we don't know whether mu lives to the far left or to the far right. It could live in this left tail or this right tail away from the given specified value mu naught. And we'll talk more about the meaning of this picture next week. But for now, just think of this as being two-tailed because there are two options. Either mu could live on the far left or the far right. Now, for this alternative hypothesis, the hypothesis is that mu is strictly bigger than mu naught. So here you're looking at a mu naught, that's sort of the assumed mean, and the alternative hypothesis is that mu is larger than that. So in other words, that mu lives over here. And this would be called a right-tailed test because we're trying to test whether the actual population mean lives over here to the far right of mu naught. Okay, and something similar can be said about this left-tailed test. Here we think that mu might be less than mu naught, and what that would mean is that mu lives somewhere over here to the left of the specified value mu naught. So this would be called a left-tailed test. Okay, and both the left-tailed and right-tailed tests are going to be called one-tailed. So let's look at some examples. Here it says the mean length of imprisonment for motor vehicle theft offenders in Australia is 16.7 months, and we want to perform a hypothesis test to determine if that mean length of imprisonment differs from the national mean. Okay, so and here we're testing it in Sydney, but that's not really going to affect our hypotheses. So I'm just going to state it this way. Our null hypothesis is that the mean in Sydney is going to equal the stated mean, which is 16.7. So that's our null hypothesis. Remember that the null hypothesis is always given by some form of equality, and usually you can sort of think of it as the boring outcome. It's just that the mean is what you expect it to be. The alternative hypothesis is the more exciting one. In this case, our alternative hypothesis is just that the mean for Sydney differs from the mean in Australia. Now, the way that I would write that mathematically is just that maybe the mean is not equal to the mean in Australia. So here we don't suspect that the mean in Sydney is going to be less than or greater than the mean in Australia. We think it could be either. So I would just write this as an inequality like that. And therefore, this would be a two-tailed test because we don't know whether we're looking at a mean that's to the left or to the right of the stated mean. So this one would be two-tailed. Similarly, in example 2, we have that the mean retail price of history books was $76.01, and we want to perform a hypothesis test to determine whether this year's mean has increased from the 2005 mean. And again, mu is going to denote this mean that we're interested in. The null hypothesis is just going to be the boring one, that the mean that we're interested in is exactly equal to the stated mean of 78.01. But our alternative hypothesis, which is what we're sort of trying to investigate, is we need to know whether this year's mean is increased from the 2005 mean. So what that would mean is that we want to know whether the mean for this year is greater than the 2005 mean, like that. So in this case, because we're just trying to investigate whether the actual mean has increased, we're not looking at a two-tailed test. This would be a right-tailed test because we want to know whether mu lives off to the right from 78.01. So this is sort of our assumed or default mean, and then we're trying to figure out whether the 2005 mean, or sorry, whether the this year's mean has increased over here to the right. So have we moved over here to the right? So this would be right-tailed. So this is how we're going to categorize these different hypotheses and their corresponding tests. Now, what I'd like to do on this last page of 8.1 is just sort of preview what we're going to be using as our technique for this hypothesis testing. So there's a lot of information on this page. I will review all of this whenever we get into next week's material, because there we're going to be applying this strategy. But here, let me just introduce sort of the terminology that we're going to be using throughout Chapter 8. So first, we'll look at the level of significance. The level of significance is the probability of rejecting a null hypothesis when actually that hypothesis was true. So there are two kinds of errors that you can make, so maybe let's jump down to this section for just a second. There are two errors. There's type 1 error, which is rejecting the null hypothesis or the boring hypothesis even when it was true. I think of a type 1 error as the sort of error that might be committed by a type A personality, if you want to think of it that way. If someone is, excitable and they're looking for something, some interesting result, then they might say, oh, actually, this alternative hypothesis is true, and they'll reject the boring hypothesis. That would be a type 1 error if the null hypothesis was actually true. And notice that this can always happen accidentally. This is not the fault of the researcher. This is just something that probabilistically will happen sometimes. So it may be the case that the actual mean in some given example is equal to mu naught, but we happen to choose as our sample a bunch of people that have an exceptionally high or an exceptionally low value for whatever variable we're looking at. So we could just accidentally commit this type 1 error. And whenever we look at the level of significance, our goal is to reduce this probability of committing a type 1 error. So this thing in parentheses here, or in brackets, is the same thing as a type 1 error. We're rejecting the null hypothesis when it was actually true, and we're trying to reduce our probability of doing that. So alpha is equal to the probability of a type 1 error. Oh no. So that's what we're trying to reduce here whenever we talk about the level of significance. And usually in these problems, we will determine a certain level of significance, or it will just be given to you. But notice that you may, depending on your field, be a little more comfortable with these large errors. So for example, if you're just talking about something like athletics, you might be okay with an error of 10%, just being willing to put up with a 10% chance that you rejected the boring hypothesis even when it was true. But if you're looking at something like whether a certain drug is safe to introduce to the population, then you would want to use a smaller value of alpha. In other words, you want to make your probability of committing this sort of error very small. So this will be sort of a contextual choice. Next, we'll look at what's called the critical region and the critical values. So I think this might be a good time to just make up an example. So let's say that you're looking at an alternative hypothesis that looks like this. So here, this would be a right-tailed alternative hypothesis. This just says, I think that the actual population mean is bigger than the stated mean. So what we're going to do is we'll set a certain level of significance, and that will be the probability of rejecting this null hypothesis when it's actually true. So in this picture, we're looking at a true null hypothesis, and the distribution that we're looking at should be the distribution of these sample means from a bunch of different studies. So in this case, let's denote by alpha this area over here. So that will be the area in this right tail. What we know from chapter 7 is that alpha is the probability that we're going to get a sample mean that lives in this right tail. So And that's assuming that this null hypothesis is true. So if the null hypothesis is true, then we only have a chance of alpha of getting an x bar value that lives over here in this right region. And this right region is what's called the critical region. So the critical region is going to be the region of x bar values, or of sample means, where we're comfortable rejecting that null hypothesis. So notice that the null hypothesis, or sorry, the null mean is sitting over here to the left. If we run a study and we end up getting an x bar value way over here to the right, we would be relatively comfortable rejecting the claim that the population mean is over here to the left. We would think that it was a little closer to the result that we got from our study over here to the right. So we'll call that the critical region. That's the region where if our x bar value falls into this region, we'll reject the null hypothesis. And the critical value is just the boundary here of this region. So this boundary, this vertical bar here, is represented by that critical value. And then a few more things that I want to define. A test statistic is this x bar value that we're computing. So whenever you run a test like this, you might sample a bunch of people and then compute a sample mean. That's a test statistic. So we just made up this test statistic to try figuring out what the actual population mean was. And then if that test statistic falls into our critical region, that means it lives, in this example, way over here to the right, and therefore we're suspicious of the null hypothesis. We think instead that the actual population mean might live over here to the right. So this test statistic is going to be used to determine whether or not to reject that null hypothesis. And then lastly, we're going to have what's called a p-value. A p-value is similar to the level of significance. It's also going to be an area, but this is going to be the probability of getting a sample statistic like the one that you got or a more extreme one. So this is the probability of getting a sample statistic like you got or a more extreme one. So in this example, I know this picture is getting a little bit messy, but bear with me. In this example, let's say that you get an x bar value like this. So this is our x bar value. The p-value here would be this shaded green area. So p is going to be the area over to the right further than x bar. That would be the probability of getting a sample statistic like x bar that's as bad as x bar or worse for the null hypothesis. So remember, the null hypothesis is that we're going to be getting an average that lives over here to the left. And therefore, if our study ends up getting an x bar value that lives way over here to the right, then we could look at this area to the right, and that would represent the probability of getting an extreme, well, I should say, an x bar value that is as extreme as our x bar value. So if we end up getting a really small p-value, or we're working with a really small level of significance, a really small alpha, and we end up falling in this critical region, then we can be pretty sure or pretty comfortable with rejecting this null hypothesis. Okay. And finding the p-values is going to be a little bit different depending on the different cases, but it's always going to look like the picture that I drew above. So if you're looking at a right-tailed test, then the p-value is going to be the area to the right of that test value, or the area to the right of your x bar. If you're looking at a left-tailed test, then you're looking at the area to the left of your test value. And for a two-tailed test, you'll need to look at the area in both tails, and we'll talk about that more next week. But notice that if you wanted to compare these areas, so let's look at the picture that I have up here. Remember that the blue region over here to the right was supposed to represent the critical region. Those are the values where we're comfortable rejecting the null hypothesis. So in other words, if our x bar value falls into this right region, then we are comfortable rejecting the null hypothesis that the population mean is toward the center here. We would have as our alternative hypothesis that we are actually getting closer to the population mean over here to the right. In other words, we're testing the alternative hypothesis that the population mean lives over here to the right. Now, in the picture that I've drawn, what we have is a p-value that's smaller than alpha. In other words, the x bar value that we found lives over here to the right of the critical value. So in the picture that I've drawn, we would reject the null hypothesis. So a way of phrasing that in terms of alpha and p is this. If the p-value that you measure, that p area, is smaller than alpha, then that means that you live in the critical region and we would reject the null hypothesis. And conversely, if that p-value ends up being bigger than alpha, we would not reject the null hypothesis. The picture for that would look something like this. So I'm going to draw it and then erase it, but the picture for that would look something like this. Let's say that our x bar value falls way over here, closer to the null hypothesis mean. Then our p-value would be larger than alpha, because the p-value would be the green area here that's larger than the area alpha. And in this case, that would mean that our x bar value lives pretty close to the null hypothesis mean, and we would not reject the null hypothesis. It still might be the case that the null hypothesis is false, but we wouldn't have enough evidence to comfortably reject it. So that's sort of the general setup in 8.1. And next week, we'll get into actually applying some formulas and determining whether we want to accept or reject a null hypothesis. But for now, I just want you to keep this terminology in mind. You don't have to worry about memorizing this terminology for now. I just wanted you to be vaguely familiar with it. Next week, we'll go over this stuff again, but with some hands-on examples.